All right, good afternoon, everyone. Let's get started. So today we are going to learn about lecture 6, the second part of the quantization lecture. In the previous lecture, we introduced the basic techniques of quantization, which is a super important technique, both in the vision age and also in the large language model age. Quantization is very widely used, no matter if you want to deploy the neural network on the phone, on the edge device, or in the cloud. This is a very useful technique. Very widely adopted in industry, and actually a big shortage of engineers currently who can specialize in such techniques. So in today's lecture, we'll first review the linear quantization, and also we'll cover two important concepts. One is post-training quantization, PTQ. The other is the QAT, the quantization-aware training. How do we fine-tune the model so that we can recover the accuracy? Remember, like in pruning, we talk about pruning and then how to fine-tune a pruned model to recover the accuracy. And similarly here in quantization, we'll quantize it and then fine-tune it, so that's QAT. And then we'll talk about binary and ternary quantization to further push the quantization bit to lower bit to only one bit. And finally, we'll introduce automatic mixed precision quantization. Not every layer requires the same number of bits. Just like in pruning, some of the layers are more sensitive, some of the layers are less sensitive, so we want to treat different layers differently to minimize the storage and maximize the efficiency. And similar case for quantization. Okay, so this is where we were left over since last Thursday. We talked about k-means. First, we started with the floating point weights, bit 32 for the weights, bit 32 for the activations. And then the second part, we quantized the weight using the k-means quantization. Okay, so for example here, this is our familiar matrix. We have a code book, and each entry we just store a 2-bit or 4-bit low precision index looking into the weight. So that's the code book. So the computation is still in arithmetic since we have to dequantize the weight into floating point. We save storage, but doesn't save the computation, which is still useful for large language model inference, batch size of 1, where it's memory bounded, not compute bounded, and weight is the memory bottleneck. So very useful technique. We are going to implement that in the lab 2. Hopefully you are all you will all download it. We have them available in our website for lab 2. Last lecture, we also introduced linear quantization. So both the weights and activations can be quantized to integer values. And the computation is also done in integer arithmetic. Okay, so we have a bias, we have a scaling factor, we derive the equation for that. So this is the k-means quantization. We have a cluster index, we have a centroid, and then we can fine-tune the centroid. We can see the accuracy is very well maintained. We can even combine proof and quantization to further push the model size to be smaller. When we are talking about linear quantization, we introduced the 0 point and the scaling factor. Okay, so for two bits, we can represent 4 numbers in 4 colors. And this is the quantized value minus the 0 point multiplied with the scaling factor, and we can get the recovered P32 weight. So remember how to calculate the scaling factor. So scaling factor basically maps the integer range to the floating point range. Okay, so this is the integer range. This is the floating point range. And this 0 point maps 0 point in integer representation into 0 in the floating point representation. And we went through all the math to calculate in a quantized matrix multiplication, so there's single layer NLP, what is the breakdown about the computation. Okay? So this is the majority of the computation done in low precision integer plus the bias. Then this can be done by linear operation and also the shift operation, and finally plus the integer add. For convolution, it's very similar. We just replace matrix multiplication with convolution. Majority of the job is done in the integer convolution. Okay, so how should we get the optimal linear quantization parameters S and Z. So we'll talk about quantization granularity, similar to pruning granularity, where we can prune a single weight, we can prune a row of weight, we can prune the whole channel or a whole filter or the entire channel. So there are different granularities for pruning, and similarly, there are different granularities for quantization. And then we are going to talk about dynamic range clipping. So we may have a pretty big dynamic range, how do we clip them? And finally about rounding, like 1.5, should we round it to 1, should we round it to 2, should we stochastically round it? We'll talk about rounding. So let's start with quantization granularity. So we'll first talk about per tensor quantization. You use one scaling factor to scale the whole tensor. Okay? So this is per tensor quantization, followed by per channel quantization. Okay? So for one channel, all the values in one channel share the same scaling factor. And which has more scaling factors? Per channel quantization, we will have, if you have like 7 channels, you will have 7 scaling factors. But here, per tensor quantization, you have 1 scaling factor for the whole tensor. Okay? And finally, group quantization. This is very important for after Blackwell architecture, NVIDIA Blackwell architecture. Group quantization is very useful for 4-bit or below. We introduce per vector quantization and also the MX data type, the shared macro exponent data type, which is a very interesting data type in lower precision. Okay, so let's start with the per tensor quantization, which is very widely used these days. So we have one scaling factor for the whole tensor, okay, using a single scaling factor for the whole weight tensor. That works quite well for large models, but for small models, people observe this degradation of accuracy. Why is the reason? What is the reason? This per tensor quantization suffer from accuracy degradation. So if we plot the channel index, and here is the range. Okay, we can see the range actually differ a lot. Some of the layers have a pretty big range, some of them have a little range. If you use the same scaling factor for these diverse channels, of course, you cannot have very good fitting for them all. So the failure comes from the large difference in the ranges of the weight across different output channels. Okay? Some of them have pretty big outliers. Outliers are the weight values that has either a very big value or a super small value compared with other values. So that causes you are wasting the dynamic range. You observe very different behavior compared with other channels. So if you use the same scaling factor across all different channels, you cannot very well represent them. So the solution is per channel quantization. We want to treat these different channels individually, okay, so that we can have a specialized scaling factor for each channel. And how does that look like? So this is our familiar 4x4 matrix, input channel, output channel, 4x4. We'll compare per channel quantization versus the previous per tensor quantization. Using per tensor quantization, we want to calculate first the scaling factor. Okay? In order to calculate the scaling factor, we want to first have the Rmax, which is the max value, the value which has the max absolute value in the tensor, which is 2.12 in this case. So Rmax is 2.12. And here we are using how many bits? 2 bits. Okay, 2 bits. So Qmax equal to 1. Okay, so Rmax divided by Qmax, using the equation we derived in the last lecture, we can find the scaling factor that map this integer range into that floating point range. So the scaling factor is 2.12. So we have the scaling factor, and now we can quantize the matrix. And since we are using symmetric quantization, so 0 point is 0. So for example, 2.09 right here divided by 2.12, that's approximately 0.9 something, is very close to 1. So quantize that to 1. This is minus 0.98 divided by 2.12. The absolute value is smaller than 0.5, therefore we quantize to 0. Okay? And on and so on. We can repeat that and quantize each value. So this is the quantized tensor. And if we can compare with the reconstructed tensor, we multiply each value with the scaling factor. Of course, the bias is 0, so we can directly multiply. So this is the reconstructed matrix. And we can calculate the difference, it's 2.28. And now let's see how does it look if we do the per channel quantization. Okay, rather than treating the whole tensor, now we treat each row, each channel individually. So let's first look at the first row. What is Rmax? Rmax is 2.09. Therefore, the scaling factor is 2.09. Second row, Rmax is 2.12. Scaling factor is 2.12, and so on. Okay, so different channels, now we have different scaling factor, which is the max value of the absolute value of that row. And now let's see how do we quantize them. Now we are using different scaling factors for different rows, okay? And so that we can quantize it in this way. For example, previously 2.09, if we are using per tensor quantization, we'll divide it by 2.12. Now we are dividing that by 2.09. It's very close, it's actually 1. Okay? And the second value divided by 2.09, the absolute value is smaller than 0.5, therefore it's rounded to 0. And this is the reconstructed tensor. Compared with the previous reconstructed tensor using per tensor quantization, now the value is more diverse. You have 2.09, you have 2.12, 1.92, etc. And the reason is that we are using different scaling factor for different channels. So actually the reconstruction error, the quantization error, is smaller than the per tensor quantization. So we just want to use this very simple example to show you the intuition where the per channel quantization can have usually have a lower quantization error compared with per tensor. And in particular, what do we see? Which one is different? So this is the quantized tensor using per channel. This is quantized tensor using per tensor quantization. We observe this value is actually different. The rest of the value are all the same, 1, 0, 1, 0, 1, 0, 1, 0. Only this value is different, minus 1, this is 0. What was the reason for that? The scaling factor, right? For example, if you look at this value, 1.03, using the per tensor quantization, it will be divided by this scaling factor, okay? Divided by 2.12. The absolute value is smaller than half. Okay? Therefore, it's quantized to 0 because the value is smaller than 0.5. It's rounded to 0 in this case. But in this case, this value minus 1.03 will be divided by the scaling factor 1.92. The absolute value is larger than 0.5, since 1.03 is larger than half of 1.92. Therefore, it's quantized to minus 1. Okay? So that's the subtle difference. You have a fine-grained, more fine-grained scaling factor compared with a single scaling factor. Therefore, the representation will be more accurate, smaller quantization error using the per channel quantization and per tensor quantization. So of course, there's a trade-off. What's bad about per channel quantization?
More values.
Right, you need to store more values, more scaling factors. Previously, you need only one scaling factor. Now, each channel you need one. So there's no free lunch. Always a trade-off. You need to store more scaling factors. Okay. So let's continue. If we want to go even lower precision, we need more accurate representation and more flexibility, right? So we can actually shrink the group size rather than per tensor, per channel, we can further reduce the group size. We call it group quantization. Okay. Using group quantization, we'll introduce the per vector quantization and also the MX data type, macro exponent data type, which is very new. So let's first motivate group quantization. So NVIDIA released this Blackwell generation GPU, which is super powerful. You can compare the performance. So comparing the H100 right here, this is GB200, Grace Blackwell 200. This is running another model. It has a very big improvement compared with the H100. The Blackwell architecture compared with the Hopper architecture. Okay. Here is 7x improvement. Okay. And on the right-hand side, we see a new data type, a new tensor core called FP4 tensor core. Okay. So these are what we are already familiar with, like FP16, DF16, 4.5 petaflops, and int8 tensor core, 9 petaops, FP8, FP6, 9 petaflops, FP4, 18 petaflops. Okay, 2x the peak throughput compared with FP8 and int8 tensor core. Okay. So Blackwell GPU introduced this macro tensor scaling so that we can maintain the accuracy of FP4 models. Okay, and in order to do that, that's basically what we are going to learn, the group quantization, having an even smaller group size to have a fine-grained scaling factor so that you can have more accurate representation using lower precision. So let's jump into that. We'll first introduce the VxQuant per vector, okay, per vector scaled quantization. So previously, we have a scaling factor for each tensor, the per tensor quantization. And now we want to have a scaling factor for each subvector, like this subvector and this subvector. Okay, so rather than R equal to scaling factor RQ minus Z, now we have two levels of scaling factor, one global and one local. This global scaling factor is a floating point coarse-grained scaling factor for the whole tensor. We also have an integer per vector, okay, fine-grained per vector for each vector, smaller granularity scaling factor. And we are going to multiply these two scaling factors together to scale the Q minus Z. So that's achieving a balance between accuracy and the hardware efficiency by the fact that we can have a more expensive floating point scaling factor, but they are at a very coarse granularity. So let's try to understand this again. Which is a more expensive scaling factor? The per tensor one or the per vector scaling factor? Which one is more expensive? This is FP16, this can be int4 or int8. So this is more expensive, right? With FP16, 16-bit, very expensive scaling factor. But we can have it as a very coarse granularity. The whole tensor have only one such expensive FP16 high precision scaling factor. Okay? Only having that is not enough. We compound that with the less expensive integer scaling factor at finer granularity. Okay? So we have a less expensive scaling factor for only low precision, but at a finer granularity. Just a couple of weights, we have one scaling factor. So that's a very smart way to have on both sides. So in order to calculate the memory overhead, let's see how that works. So we have a 4-bit quantization for the weight. We have 4-bit per vector scale. So this is 4-bit per vector scaling factor for every 16 element. So this is 16 element right here. And we also, what is the effective bit width? So each value is represented in 4 bits. And then we also have a 4-bit scaling factor for every 16 elements. Okay, so the 4-bit scaling factor is amortized across 16 different elements. plus the original 4-bit. So it's altogether 4.25 bits. So that's the way to calculate the overhead of two-level scaling. So in that context, we can have multiple levels of scaling factor. Okay? We can have the first level 0, level 1. We can continue different levels. So let's see what we have learned so far. How does that fall into this big picture? We introduce this per channel quantization. Okay, we have a scaling factor L0, level 0 scaling factor for the whole channel. So the data type for the weight in red is int 4, and then the group size L0, level 0 group size is per channel. The whole channel share a FP16 scaling factor. So the effective bit width is 4. Since we have 4 here, and assuming we have many channels, tens of thousands of channels in large language models, this FP16 divided by 10,000 can be negligible. So effective bit width is roughly 4. And in VSQuant, okay, in VSQuant, the data type is also int 4. So each value is 4-bit, and then the L0 group size is 16. So that's mean every 16 elements we have a scaling factor. And the scaling factor is unsigned int 4. Okay, and the next level group size is per channel. The whole channel also share FP16 scaling factor. So what is the effective bit width? 4-bit, and then another 4-bit scaling factor, but shared by 16 values. And this FP16-bit can be divided by tens of thousands. That can be ignored. So we have 4.25. That's the effective bit width. So now comes the famous MX4, MX6, and MX9 data type. Okay. So let's start with MX4. So the data type is S1, M2. Remember in the last lecture, we have one sign bit, we have two mantissa bit. What is missing here? The exponent bit, right? Where is the exponent bit? Actually, they are here. So we have one exponent bit that is shared by 2 values. Okay, we have 1 bit shared by 2 values. We also have an 8-bit scaling factor, and this E8 only exponent, okay, shared by 16 values. So these are the 2 levels of scaling factor. And now we can quickly calculate what is the effective precision bit width for MX4. 1 bit for sign, 2 bit for the mantissa, 3 bits, right? And then we have 2 bits shared by 2 values. Oh, sorry, we have 1 bit right here, E1, 1 bit shared by 2 values, so that's half a bit. And finally, we have 8 bits shared by 16 values, that's another half bit. So 3 plus a half, that's altogether 4 bits. Okay, that's why we call it MX4. We also have MX6, which has 1 sign bit and 4 mantissa bit. That's 5 bits altogether. 1 exponent shared by 2 values, and 8 exponents shared by 16 values. So 5 plus a half, that's 6. And similar for the MX9. Okay, MX9 we have 1 sign bit, 7 mantissa bit, 8 bit here, and then we have 1 bit of exponent shared by 2 values, group size of 2, and then 8 bit of exponent shared by 1 group size, which is 16. So that's 8 plus a half, that's 9 bits. So these are the more fancy representations going lower precision, and group quantization, which is super helpful to maintain the accuracy for such fine-grained quantization granularity. All right, so let's switch gear to talk about next topic, about dynamic range clipping. So dynamic range matters a lot since it can change across different inputs. Some of them may be large, some of them may be small. But how do we determine the dynamic range? Because that's very crucial since the scaling factor is calculated by dividing the dynamic range between the quantized value versus the floating point value. So given a bunch of images, they may have very different dynamic range for each. So to determine the floating point range, the activations, we need to gather the statistics before deploying the model. And there are generally two methods, two ways to calculate the dynamic range. So if the model is trained by yourself, so if you train the model by yourself, if you have access to the training recipe, during training, we can actually calculate the dynamic range by maintaining a EMA, the exponential moving average. And what is that? We maintain this Rmax and Rmin, which is Rmax, Rmin, across different iterations. So at t minus 1, this is t, this is t. So Rt basically equal to alpha Rt plus 1 minus alpha Rt minus 1. Okay? We are using this discounting factor to discount the previous dynamic range with the current dynamic range. Okay? So the larger the alpha, the more we are using the recent dynamic range. Okay? So we smooth the dynamic range by using alpha. What is the extreme case? Alpha equal to 1, right? If alpha equal to 1, we are not using any of the old dynamic range because this term becomes 0, okay? So that's the intuition. But that is only possible if you have access to the training process, if you train the model by yourself. If the model is trained by somebody else, we don't have access to this whole training process. Therefore, it's very hard. It's not possible to estimate the dynamic range in that way. But that is the most common case. Sometimes we just download a model from Hugging Face, we quantize them, we deploy them. Then in that case, how do we get the dynamic range? We want to maintain a calibration batch, calibration data set, and just use that calibration set, like a bunch of images or a bunch of text, to calculate to estimate the dynamic range. We can use the dynamic range for in this calibration set to represent, to assume that is representative for the input images or text from other sources. Okay, so by running the calibration batch, we have two ways. Try to find the Rmax. Okay, we probably don't want to use the full Rmax, so actually there is a trade-off here. Say this is the distribution of the activation. Okay, we observe there is a very long tail of distribution. Some of the values are super big, but you have a very small amount of big values, very small amount of these very negative values. So if you set the mean and the max to be like here versus here, you have a big waste. You are wasting lots of the representation because you have only very few values in the extreme corners. So assuming we want to push the mean and max to be somewhere here where there are at least some weights, because if you squeeze it closer, the distance between each quantization boundary will be smaller, and the representation for these values in the middle, will be more accurate if the quantization distance between adjacent bucket will be closer, right? So there is a trade-off. The mean and max, you don't want it to be like the exact max and mean value. You don't want it to be very small, but there might be a sweet spot. So if it is a Laplacian distribution, we have closed form solution to find the sweet spot. Okay, for 2-bit, that is 2.83b. For 3-bit, it is 8.89b. Okay, so that b is the Laplacian parameter, can be estimated from the calibration input distribution. But this is a very rare case. Very rarely the input follow this Laplacian distribution. So what should we do if if it doesn't follow the Laplacian distribution? So a very widely used technique is to use the KL divergence method to calibrate the range. So we want to minimize the loss of information. Okay, since the integer models encodes the same information as the original floating point model, so we want to find the dynamic range by minimizing the KL divergence. So this is the equation for these two distributions, P and Q. One is before quantization, one is after quantization. And we find the mean and max value such that it can minimize this KL divergence. Let's give some intuition. Say this is the distribution. This is distribution of the activation value. This is absolute value, ranges from 0 all the way to 400. Some of them might be even 480. But most of the value, okay, so this is the normalized number of counts. Okay, so loss of value is actually below at 40, and then has this long tail. If we decide to set the max value to be here, what happens? So all the values above, all the values in this long tail will be clipped to this value, roughly 50, okay, roughly 40 or 50, right? All the value above 50 will be clipped to 50. And the count will be the sum of all these values count. So it'll be this is the count. Okay, so this is before and after the finding the max value using the minimizing the KL divergence. What happens if you have a larger max value? So you will have a shorter tail on the right hand side, and the value near the quantization, near the max value will be more accurate. However, the range will be larger. Therefore, these values, we actually have a lot of them, will be less accurate because the dynamic range is now larger and the quantization area is now larger. It cannot be too small, it can be not to be too large. The best way to calculate that is by minimizing this KL divergence. And let's see some other examples. So AlexNet, Resident 152, GoogleNet. So this is the clipping, the optimal clipping range discovered for these different models. Okay, none of them is the largest value. They are not using the largest value. This is the largest value. But they are using somewhere smaller than the largest value. We just clip the largest value to be the quantization max. So this figure further illustrates the intuition between why we need such kind of clipping rather than using the max value. Okay, so if we have such a distribution, very long tail, if we choose the mean and the max according to the real mean, this is negative 0.8, this is positive 0.8. If we choose the max and mean this way, this will be your quantization range. And you can see the quantization noise is pretty large because the adjacent quantization centroid, the distance is pretty far from each other. And in particular, you have very low density data. Just a few of them is in this big range. Versus we can clip it. Okay, this is the new mean, this is the new max, and this is the new dynamic range. And the distance between adjacent centroid becomes much smaller, right? Much smaller compared with this one. So the quantization noise becomes much smaller. And all these values will be clipped to here. That's still okay. Why? Because you just have very few of them in this range. Very few of them in this range. So it's fine to clip them to the desired max value we want. And this is actually a quite helpful technique, very widely used. So on the right-hand side is showing the animation. This work is called Octal from NVIDIA. It can automatically find the optimal clipping range. And on the left-hand side is showing that the mean square error is convex. Okay? It cannot be too the clipping scalar cannot be too small or too large. If you're too small, you waste a lot of the. If you're too large, you waste a lot of the dynamic range. If you're too small, then many values will be clipped to the boundary. So there's it's convex. There's a sweet spot in the middle, and you can use this technique to find the optimal clipping range. And after applying Octal, you can see the accuracy can be very well maintained compared with the IP32 accuracy. Okay. So finding the granularity, very important, and then clipping is very important. Okay, any questions so far? Yeah.
I understand how you use KL divergence to measure the loss of information and to sort of prevent a clip that's too large, but how would you encode the target of trying to minimize the number of values? Like there has to be
The value is the determined. If you have 4 bits, you have 16 values.
Okay, so you just determine one type of quantization, then you minimize information loss for that one type.
One type, yes, correct. All right, if no question, let's take a quick break and come back in 5 minutes to continue discussion about rounding. All right, welcome back. Let me turn on the mic so you can hear me. All right. So let's jump into the third part of quantization about rounding. Okay? So this is our conventional wisdom. If you have a vector 0.3, 0.5, 0.7, 0.2, you want to round it to like 0, 1, 1, 0. Okay? So just round the nearest. But contradictory to our conventional wisdom, rounding to nearest is actually not optimal. So weights are correlated with each other. The best rounding for each weight to the nearest is not the best rounding for the whole tensor. Okay? So sometimes we want to have some randomness. For example, the same tensor sometimes like 0.5. If you round it to 0, if you round it to 1, not necessarily rounding it to 1 might be the optimum. Sometimes we can even round it to 0. Okay? So such stochastic rounding usually helps during the quantization process. So instead of rounding to the nearest, we want to choose rounding down or rounding up stochastically to get a better reconstruction. We can also learn a delta, okay, between 0 and 1. We added to the original weight and then we rounded to the nearest. For example, rather than just finding the nearest, rounding to the nearest, we can add a value. This value would be learned when we pass it through a function. H is a function to map v to the range between 0 and 1. Between 0 and 1, this is a possible solution using such rectified sigmoid. So the HV is between 0 and 1. We add it to W and then we round it to the nearest, so that we can learn a tensor with the same dimension. Okay? So this V is a random variable of the same shape, same dimension, followed by a regularization term encouraging the HV to be binary between either 0 or 1. Okay? So this is called Alan Round, very popular paper, helping recover the accuracy. So just intuition is that don't just round to nearest. Usually you can apply some stochastic to add some randomness during the rounding process. Usually helps. So let's do a quick summary about linear quantization. What we have learned so far. We learned about 0 point, scaling granularity per tensor, coarse grain per channel, or group quantization. After below 4 bits group quantization is getting super popular, super important. MX4, MX6, IP4, etc. Range clipping, we can use different techniques to find the optimal range to clip it, and then rounding techniques. So by applying these techniques for the weight, for the activation, we can actually very well maintain the accuracy for a bunch of models, like GoogleNet, ResNet. However, some of the smaller models, like MobileNet, they still suffer very heavy accuracy degradation, even after applying all the techniques we have learned so far. Like 10%, 2% degradation of accuracy, which is quite bad. So what should we do? So let's talk about fine-tuning techniques to recover the accuracy for these models. So let's talk about QAT, the quantization aware training. A very simple technique was already introduced in the last lecture about using k-means quantization, where we have a code book. After we get the gradient, which is of the same size as the weights. So this is the weight, this is the gradient, the dimensions are exactly the same. We sum the gradients corresponding to the same color, the same centroid, sum them up, multiply by the learning rate, subtracted from the original centroid to get a fine-tuned centroid. So that's very simple for the k-means quantized neural network, where we are just updating the centroid, it's updating the code book. It's getting more complicated if you're doing linear quantization. Okay, so in the linear quantization, the weight and activations are all low precision. Okay, int8 or int4 or IP4. In that case, during the training process, we actually maintain a full precision weight in the back. Okay, maintain a full precision, not 4-bit, not 8-bit, but 32-bit or IP16 or 16-bit, a full precision copy of the weight in the back throughout the training, so that we can accumulate very small gradients, very small changes, accumulate that in the weight without loss of precision. Okay, and once the model is fully trained, this FP32, this full precision weight can be thrown away. We only keep the quantized weight deployment time. So this is the layer n-1, layer n+1. These are the activations, these are the weight. The weight will be quantized. This is the full precision weight in the back, quantized, feed it to calculate layer n for the conv, bn value, and then get the output for the next layer. Okay? So for the backward process, we update this full precision weight so that we don't lose any precision. And remember, during the activation, here we calculate the activation and we should quantize that activation so that at the boundary of the output, the value is quantized. So this whole process is called simulated quantization or fake quantization during the training process, because the weight is quantized to QW, but it's still using a 32-bit floating point register to represent that value. Although the value itself is quantized, but we are still using a floating point number to store it. So we train the model taking quantization into consideration by adding these two quantization nodes, compute node. One is quantizing the weight, the other is quantizing the activation to simulate this quantization process. So we have QW here, and we have QY here. So forward process is very simple. We have QW, we have QY. What about the backward process? How does the gradient flow to the weight? Because the quantization, this is basically the quantization and activation, if you think about it as an activation function. Okay? So below 0 and 0.5 is all 0. Between 0 and 5 to 1.5, they are 1. Between 1.5 and 2.5, they are 2, right? So it's actually a step function. So the quantization makes the input value to be discrete. Okay, the output is discretized. What's the problem here for the gradient? The gradient is all zero, right? Gradient becomes zero. Then we can learn nothing if you have a zero gradient. So actually we are using a technique called straight-through estimator, STE, straight-through estimator. We simply pass the gradient through the quantization as if it has never been quantized, if it is just an identity function. Okay? So the gradient to the weight is the same as the gradient to the quantized weight. You treat the gradient of the quantized weight versus the gradient of the weight to be exactly the same. So this is the quantization compute node. This is quantized W, this is W. Okay? So you treat the gradient between this purple line and this purple line to be exactly the same, as if it is just an identity function in this blue quantization node. And what happens becomes an identity function, okay? Making the gradient calculation much easier. So this is the full picture. Okay? So the purple line is the backward pass. During the backward pass, before and after the quantization node, the gy is exactly the gradient of the quantized y. And here, the gw is exactly the gradient of the quantized w, as if this blue quantization node is an identity function. So we can use this straight-through estimation technique to estimate the gradient for the floating point weight and floating point activation. By using quantization aware training, so here are the quantization aware training results, here are without the quantization aware training, we can compare the accuracy. It's drastically improved a lot. So per tensor quantization improved from 0.1%, almost nothing, to 70%. Per channel quantization, originally it's better, it's like 59%, now it becomes 70%. So this quantization aware training really plays quite a helpful role in the accuracy recovery. Some of the models like NASA and Mobile here, the original accuracy is already pretty good. So the quantization aware training gives some marginal improvement. But for large language models, which is very costly to train, it'll be the desired scenario will be like this. Okay? Just using post-training quantization without any fine-tuning, the accuracy should be very good. We'll cover that in the large language model section in details. Okay, so that concludes the linear quantization part. Can we go even smaller? Okay, so we'll introduce binary and ternary quantization. Just use 0, 1, maybe -1 to represent the weight and activations. And let's see what kind of magic we're having here about binary and ternary quantization to further push the quantization precision to only 1 bit. So let's see an example. So weight dot product with activation, 8 times 5 minus 3. So this is the weight, this is the activation. And we assume the binary is 1x, computation is 1x. Each operation is plus, add, and also and multiply and accumulate. We can quantize the weight to be binary. Okay? Rather than 8 minus 3, 5 minus 1, we have 1 minus 1, 1 minus 1. So we binarized the weight. If it is positive, then it's 1. If it's negative, then it's minus 1. So we no longer have any multiplications, but everything is plus or minus. So the memory is 32 times smaller for the weight. Previously we did 32-bit, now you need only 1 bit, plus 1, minus 1. And the computation is roughly 2x, less flops, because previously you have multiplication, now you have no multiplication, only add. So how do we do that? One way is to deterministically binarize that. If the weight is positive, then it's plus 1. If it's negative, then it's negative 1. That's basically the sign function. Very straightforward, but you can imagine this results in a big degradation of accuracy. Just now we mentioned adding some randomness usually helps with quantization. So we can do stochastic binarization. Like in this equation here, if it's smaller than -1, it's deterministically to be 0. If it is above 1, it's of course 1. But between -1 and +1, sometimes it can be -1, sometimes it can be quantized to +1. If it is 0, you have half probability to be quantized to 0. You have half of the probability to be quantized to positive. Okay? And can have a linear interpolation between -1 and +1. But it's harder to implement since we need the random number generator in hardware. That's not straightforward. So let's see what happens to our familiar matrix. This 4x4 matrix we use many times. If we binarize them to 1 bit, just using the sign before and after, the accuracy degraded by a big margin. Okay, degraded by 21%. And the quantization error is 9.28, pretty big quantization error. And what happens if we do some trick? Okay, so we can have a scaling factor. Okay, we have a floating point scaling factor, which is alpha in this case, to make sure the sum of all the values, the absolute value, the sum of the absolute values of all the elements stays the same. So here, the scaling factor will be calculated by the L1 norm, which is the sum of the absolute value divided by n, since every entry, the absolute value is 1. So we have n elements, 16 elements in this case. Then we can just calculate the alpha, actually to be 1.05, okay, which is equal to the L1 norm divided by 16 values. And if we multiply this scaling factor, we can see the quantization error slightly decreased. And the accuracy delta actually improved a lot. Actually becomes 0.2%, a positive 0.2%, which is very interesting. So just now we binarized only the weight. Now we want to binarize not only the weight, but also the activation. Okay. So let's see what happens if both the weight and activation is binarized. So we have 1 times 1, that's 1, 1 times -1, that's -1, -1, -1, that's 1. Okay, so this is the truth table. Let's see another operation, which is XOR operation. Okay, XOR operation. If this both values are the same, 1, 1, 0, 0, then the output is 1. If the two inputs are different, 1, 0, 0, 1, then the output is 0. So that's the XOR operation you might have learned in 6.191. So what's the relationship between binarized weight and activation versus the XOR operation? Actually, they are heavily correlated. So if we sum them up for the XOR results, okay, so this is 1, XOR with 1, this is 0, XOR with 1, 1, XOR with 0, 0 XOR with 1, you can get 1 plus 0 plus 0 plus 0, that's 1. So naively doing this actually doesn't help. It's minus 2 versus 1, they're not the same. So what's the relationship? How do we use XOR operation to implement the binarized weight and activation? Since XOR is just so simple to implement in hardware. So let's see, how do we match them? So assuming everything is -1, okay? So since the smallest value is -1, okay? If we have everything is -1, if everything, we sum them up, that's actually -4. And but here, if we multiply the sum of the XOR results with 2, okay, so this is the sum of the XOR result, which is 1 times 2, or times 2 can be very efficiently implemented by shift to the left for 1 bit. Okay, if -4 plus the count times 2, that's -2. That's exactly the value on the left. Okay, so take another look. Assume everything is 0. Okay, we just count the number of ones in this case. Because only if both values are the same, then it's 1. Otherwise, it's 0. Okay, if it is 0, it's corresponding to everything on the left is minus 1. So that's why we assume if everything is minus 1 and add the difference. The difference, how do we calculate the difference? Is the number of ones, in this case, times 2. Okay, so the difference between minus 1 and plus 1 is 2. So we have 1 more, you add 2. You have 2 more, you add 4. You have 3 more, you add 6. Okay, so you just count how many values are 1 and then times 2. Okay, and then you can match the left and the right hand side. So put it in math. It's equal to minus n. N is the number of elements. In this case, we have 4 elements. 1, 2, 3, 4. Minus n times plus 2 times the sum of the XNOR operation. So minus 4, since we have 4 entries here, we calculate the XNOR, sum them up to be 1 times 2 and add minus 4. So that's minus 2. So we can use this very simple XNOR operation to calculate the scenario where both the weight and activations are binarized. And this count operation has a name, it's called pop count. Okay, return the number of ones in this array. Okay, the array is binary, either 1 or 0. The pop count operation is basically applying on this binary array and count the number of ones. Just return the number of 1. It's called pop count. So using the pop count function, the final result would be minus n plus pop count shifted by 1. So shifted by 1 is basically multiplying by 2. Okay, using that, we can easily calculate the dot product very easily. So for example here, this is the original floating point unquantized weight and activation. This is the quantized weight and activation. We just do the XNOR operation and then shift it by 1 and then plus 4, so that's the result. So the operation, rather than multiplication and add, now it becomes XNOR and pop count. Both are very cheap to implement in hardware. The memory is 32 times smaller since both the weight and activation becomes 1 bit. And the computation is roughly 58 times less. Why is that? That's roughly the arithmetic, that's roughly the complexity between XNOR pop count operation versus MAC operation. So in that way, we can use very cheap hardware. You no longer need to have multipliers or adders. You just need to have the XNOR and pop count operations. And what is the accuracy? So if we only quantize the weight, leaving the activation to be 32-bit, you have a little drop of accuracy. If you have both the weight and activation to be binarized, actually a big drop of accuracy. But if you use the XNOR net and the XNOR operation, the accuracy is improved, but still very noticeable degradation of accuracy. And if you want to see actually a detailed implementation, I actually did one repo, open source repo on FPGA. Only use these 2 operations. One is XNOR operation, the other is the pop count operation. We synthesized that, we wrote a very long, we synthesized that, we open source that. It can be deployed on an iStick FPGA, very small FPGA. It's open source on our GitHub. Feel free to check it out. Okay, so since the accuracy is too low here, okay, can we do better by using, give it 1 more centroid, give it a 0, right? Rather than -1 and +1, let's have a 0 and make it a ternary. So ternary weight networks, the weights are quantized to +1, -1, and also 0. So we have a threshold. Above the threshold is positive, between that is 0, below the threshold is minus. Okay? And how do we calculate delta? So there is an empirical value. You find the distribution about the absolute value, and then multiply by 0.7. So that's purely empirical. And use that to determine this threshold. Okay. So given this is our familiar weight matrix, and then we calculate the threshold, 16 entries, you sum them up, and then times this empirical 0.7, so delta is 0.73. So use that as the boundary. 2.09 is above the boundary, so it's quantized to +1. Minus 0.98 is below the boundary, so it's quantized to -1, and so on. Like this 0.09 is between the minus and positive boundary, so it's quantized to 0. Okay, we can also find the scaling factor. Okay, find the scaling factor such that the sum of the absolute value remains the same between the left and the right. And so here, the scaling factor is calculated as 1.5 because this is the counting the number of non-zero elements and divided by the number of non-zero elements here, which is 11. In that way, we find the accuracy can be improved from 60 to 65, but still there's a gap with the full precision, 69. So how do we further improve that? So rather than using the heuristic, we can also train, rather than using this fixed scaling factor, we can use two trainable parameters, the positive weight and also the negative weight, to represent the positive and negative scales in the quantization. So this is the original full precision weight. We normalize them to be between -1 and +1, and then we find this threshold to be t, and then we quantize them, and then we scale them by two learnable scaling factors, W positive and W negative. So the final weight becomes minus W negative, 0, and positive W positive. We can train these Wn and Wp to improve the accuracy. And finally, the accuracy in TTQ further improved on top of the 2-bit TWN to further match the original full precision model. So there's some tricks we can play for ternary neural networks. So this is the big picture. We started with floating point weights, floating point arithmetic, and then we talk about this k-means quantization. Now we have integer weights plus a floating point codebook, and still using floating point arithmetic. And then we have, this is probably the most popular, linear quantization. We have integer weights and also integer arithmetic. We talk about a lot of techniques to find the granularity, to find the clipping, etc. And finally, we have this binary and ternary quantization. We have binary and ternary weights using bitwise operations. But here, I want to point it out that not necessarily the lower the better. There should be a sweet spot, and roughly 4-bit is commonly a great sweet spot these days. It might get lower in the future, but there is a trade-off, right? So the arithmetic intensity matters a lot for hardware efficiency. So you have more compute, you might be memory bounded. So if you're going, when you are reducing the precision, the memory footprint decreases linearly, but the compute, the actual model expressiveness, the bitwise operations actually reduces quadratically. So the compute reduces faster than the memory. Okay, the memory reduces slower, and the memory is more expensive than the compute. Therefore, the expensive stuff is reducing slower. The cheap stuff is reducing faster. So there is an imbalance. You get diminishing return after that. So that's something to pay attention when you are reducing the precision. And usually you don't want corner one design knob to the extreme. You want to utilize all the design knobs. For example, pruning, quantization, distillation, neural architecture search, all different techniques together. All right, lastly, just like we talked about the sensitivity analysis for pruning, where different layers may have different sensitivity. Some of them you have higher pruning ratio, some of them may have lower pruning ratio. That's actually the similar case for quantization. So here we have 3 layers. They are all quantized for the weight and activation, all quantize the same number of bits, all 8 bits. We can also do mixed precision quantization. Okay, so for some of the layer which is more sensitive, like this layer, we use more precision. Some of them is less sensitive, like here and here, we use fewer precision. There are a lot of choices, right? From 1 bit to 8 bit, you have 8 choices. For weight and activation, you have 64 choices. And you have n layers, that's 64 to the n number of design. The design space has so many choices, 64 to the n choices. You can use different techniques to search in this large search space. Here in this paper called HAQ, Hardware Aware Automated Quantization with Mixed Precision, we use this actor critique model, our agent, to search that. We map it to the hardware, and then we get a direct feedback, including the latency and the energy, so that we can feedback the reward to the actor critique model and to give the next generation of action. I think that's overcomplicated, but that's rule of thumb is that you want to have different, sometimes you want to have different precision for each layer. Some of them you can keep them in FP32 or FP16 if it doesn't quite hurt your accuracy, like some of the very cheap layers, or some of the memory bounded layers. Right? For some compute bounded layers, you definitely want to have a lower precision and make sure they have they are less sensitive to the accuracy. So this is a trade-off between the latency versus the accuracy in the design space, right? So this is linear, uniform quantization versus using the hardware-aware quantization. You can see the hardware-aware quantization, given the same latency, it can have a higher accuracy, and given the same accuracy, it has a lower latency. And using that technique, we can also optimize for different design targets, which we are going to cover in the neural architecture search section. Okay, we want a model to have smaller model size, to be faster, to be energy efficient. Right? So using such automated approach, hardware awareness, we can optimize not only for the model size, but also for the latency and also for the energy. All right, in summary, in this lecture we reviewed linear quantization, and then we introduced post-training quantization techniques. We introduced different granularity of quantization, the per tensor, per channel, group quantization, in particular FP4 and also MX4 data types. And also we talk about how to determine the dynamic range, the clipping, the rounding techniques. Next, we talk about these quantization-aware training techniques to use fine-tuning to recover the accuracy. In particular, this straight-through estimator, to use STE technique to fine-tune a quantized model. And then we introduced binary and ternary neural nets, just use 1 bit or 2 bit to represent the weight and activation. In particular, use pop count and XNOR operation to deal with the binary quantized network. And finally, we talk about automatic mixed precision quantization. All right, so that's the end of this lecture. In the next lecture, we'll talk about neural architecture search. And lab 2 is released, so welcome to try it out. Thank you.